This is part 7 of the series Integration, and we're going to start this part with one final problem in finding the area of a region bounded by a graph of a function. This time we're going to be looking at using horizontal rectangles instead of vertical rectangles. In our previous examples, all of our rectangles have been taken with respect to the x-axis. That is, we had the width of each rectangle was a delta x value. In this case, we're going to be using a delta y value. So we're going to be going from the x-axis up. And so the concept, other than that, is basically the same. The difference is we're just kind of turning 90 degrees here. So in this case, we're going to be looking for a delta y sub I and a point on the y-axis that we're going to call y sub I, which is a point within each one of these vertical subregions. So let's start off. We're looking for our delta y sub I, and it's important to note before we go any further that your function must be in terms of the variable y, as opposed to before we had the equation in terms of the variable x. Now we're going vertically, so we need the equation in terms of y. So our delta y sub I is b minus a over n. Nothing's changed there. The difference is that the b minus a, the a value is the lower limit on the y-axis, and the b value is the upper limit on the y-axis. So it's 1 minus 0 over n, which is 1 over n. And our y sub I is going to be the same basic idea, a plus I times the width of each subinterval, 1 over n. Since a is 0, this is actually going to be I over n. So now we can put it into our limit form. The limit as n approaches infinity of the sum I equals 1 to n of y squared, so it's this value squared, I over n squared, times delta x, 1 over n. And so now, just as we've done in the past, we combine our terms. So we have I squared over n squared times 1 over n, which gives us I squared over n to the third. And here we're going to take our limit as n approaches infinity, and the sum is carried through to the sum of I equals 1 to n of this. Now, as usual, we can pull out the n term, so it's 1 over n to the third times the sum of I equals 1 to n of I squared, and that limit is carried through. To evaluate this sum, we have 1 over n to the third times n plus 1 times 2n plus 1 all over 6. And working this out, we end up with 2n to the third plus 3n squared plus n over 6 times 1 over n to the third. And simplifying that further, if we take a look at these two values, the first coefficient is a 2, so that's 1 third plus n squared over n to the third is 1 over n. 3 over 6 is 1 half. So it's 1 over 2n plus 1 over 6n squared. We're going to go ahead and carry this limit all the way down. So we take the limit here, limit as n approaches infinity. This term goes to 0, this term goes to 0, so we're left with 1/3. So the only thing that really changed in this exercise was the fact that we were dealing with horizontal rectangles instead of vertical, and we were taking a function with respect to y as opposed to x. So everything else is the same. You just have to make sure that you're being consistent with your variables. So let's move on to the next section and see what we have in store. We're going to start this section with a formalization of the concepts that we've been working with up to this point. We have been working with something called Riemann sums, and we're going to present a formal definition of it here. But before I get into that, just a very basic idea of what a Riemann sum is when we take the sum of the areas of rectangles in a particular region, Riemann sums tell us that the rectangles themselves can be of different widths, and when we find the value within each subinterval that we evaluate the function at, it can be at either endpoint or any point in between on that subinterval. It doesn't matter what point we choose in the subinterval to evaluate our function at. In other words, what we use for the height of the rectangle. So those two things are central. The fact that the widths of the rectangles can be different and the value we evaluate the function at within each subinterval can be different. So formally, it says, let f be defined on the closed interval AB, and let delta be a partition of AB given by A equals x0, x1, all these are less than your actual value to B. In other words, any point within that region where delta x sub I is the width of the ith subinterval, that is, the width of that particular rectangle. If C sub I is any point in the ith subinterval between x sub I minus 1 and x sub I, so any point in the subinterval, then the sum of from I equals 1 to n of f of C sub I delta x sub I is called a Riemann sum for the partition delta. So this is exactly what we've been working with up to this point for both this type of function and the vertical functions. They're all Riemann sums. Now, if we extend that one step further, the width of the largest subinterval of a partition, assuming that they're different, is called the norm of the partition, and it is denoted by these double vertical bars and the delta symbol. If every subinterval is equal in width, which is what we've been dealing with so far, the partition is regular, and the norm is given by our basic delta x, which is just b minus a over n. We've seen that several times. So what we've been dealing with is regular partitions using Riemann sums. And we're going to see, because of the fact that we're taking the limit of this sum, it really doesn't make any difference what the width of each subinterval is, whether or not it's regular or irregular, and where we pick the point inside that subinterval. So that's what Riemann sums are. Now, when we go ahead and take the limit of a Riemann sum, we come up with a brand new quantity here, the definition of a definite integral. If f is defined on the closed interval AB, and the limit of Riemann sums over the partition delta, this limit exists, that is, the limit as the norm of the partition approaches 0. Now remember, the norm of the partition was the width of the largest subinterval, and when the width of the largest subinterval approaches 0, in essence, what you're doing is you're driving the number of subintervals to infinity. So it's accomplishing the same exact thing. But in this definition, the limit of the norm goes to 0 of a Riemann sum, then the f is said to be integrable on the closed interval AB, and the limit that we've just seen here is denoted with our antiderivative sign, the integral sign, with two numbers added. A is the lower limit of integration, and B is the upper limit of integration. And it's the integral of f of x with respect to x. So what we've done is we've created a new quantity, and remember that when we dealt with antiderivatives, we had just the integral sign, and the result was a family of functions. With this limit and the definite integral of f from a to b, with a as the lower limit and b as the upper limit, the definite integral results in a number, as opposed to the indefinite integral, which is the antiderivative, results in a function or family of functions. So the definite integral gives us the area under the curve, and the if indefinite integral gives us a family of functions. So let's see if we can put this into practice. So in this example, we want to evaluate this definite integral, and that is to find the area between the curve and the x-axis. And so we're going to use the limit of a Riemann sum. So the limit as the norm of the partition goes to 0 of the sum as I goes from 1 to n of f of x sub I delta x sub I. So as we stated in the definition of definite integrals, as this norm of the partition goes to 0, the number of subintervals is going to infinity. So this implies the limit as n approaches infinity of the sum of I equals 1 to n of this quantity. Now before we can actually do this, we actually need our delta x sub I. So our delta x sub I is b, which is 1, minus a, which is negative 2, all over n, which is going to give us 3 over n. And so that implies that our x sub I is going to be a, which is negative 2, plus 3I over n. That is I times delta x sub I, which we could work this out. This is negative 2n plus 3I over n. So that gives us this sum, 2 times negative 2n plus 3I over n times 3 over n. So this was our f of x. 2 times this x sub I went in for the x, and we multiplied by our delta x sub I, which is that. So I'm going to do a quick sleight of hand to get to the bottom of this. So we multiplied through by the 2. Here we multiplied by the 3 over n, and we separated these two terms out as two separate sums. So the 12 over n becomes multiplied by the sum of 1, and then 18 over n squared times the sum of I. This is the sum of n, or sum of 1, and this is the sum of I. Multiply through, simplify, and we come down to our final limit where this n term goes to 0, so we have negative 12 plus 9, which gives us a negative 3 for the area under a curve. And that makes sense because it appears that there's more of this negative quantity than there is of the positive. So it looks like the measures match. So let's move on and take a look at another example.